A gwyniwch agus a cordia, is mis an talamh pádraig ó gaire, uachtarán agad a bhríoga na hÉireann, agus tá an áthas orm fáilte a curráibh go léir inniu. So good evening everybody, my name is Pat Gyrey and I'm the President of the Royal Irish Academy and it's a great pleasure to welcome you here this evening for the Hamilton Lecture 2024. This event is organised by the Royal Irish Academy with generous support from IBEC and media partner The Irish Times. So on the 16th of October, which is why we have this event today, on the 16th of October, but all the way back in 1843, not many of you would have been alive then, I don't think, but nevertheless, 1843, a long time ago, Sir William Rowan Hamilton, a former president of the Royal Irish Academy and a member of staff in Trinity College Dublin, discovered quaternions. So quick question now for the audience. Just how many people here know about quaternions? Okay, so the mathematicians are all out in force tonight. That's good to see. That's good to see. If not, I hope you'll learn a lot. I'm not a mathematician. I'm only a mere chemist, so I'll learn a lot about quaternions. I have learned a lot, but I'll learn more about maths this evening as well. But while walking from the Royal Canal, along the Royal Canal, I should say, from Dunsink Laboratory to an Academy meeting, he had his eureka moment, of course, where he then decided, well, if I don't write this equation down now, I might forget it. So he sketched it on Broom Bridge. And that is now a national monument, as you know, which has been carefully renovated. And that's all very important for the mathematical community and indeed for the Irish scientific community. So each year the Royal Irish Academy commemorates Hamilton's contribution to mathematics by celebrating Hamilton Day. We do this because Ireland has a rich history of scientific excellence that should be celebrated and recognised. So we're a nation of saints and scholars, but we're not just artists and musicians. There's some very famous scientists as well. So Hamilton will be one of those, and as a chemist I would of course have to say Robert Boyle, the father of chemistry, who grew up in Lismore Castle all the way down in Waterford, is a very famous person in my world, so to speak. Indeed, only today a plaque marking the birthplace of William Rowan Hamilton at 38 Dominic Street was unveiled by Dublin City Council. And we certainly thank the Dublin City Council for that. That's a really important thing as well. Although we look to the past to commemorate Hamilton's achievements, this event is also an opportunity to look to the future and to recognise the next generation of great Irish mathematicians. So earlier today, at about 4:30, as it turns out, that time difference, we presented the Hamilton Prize in Mathematics to the top students of mathematics in their penultimate undergraduate year, as nominated by 9 higher education institutions on the island of Ireland. Some of them have had the opportunity to stay for the lecture, so perhaps if you could just raise your hand so we can see where you are. Many of them. One here, some around the back. Good, well, you're very welcome. Congratulations. So we're also delighted to welcome the recipients' families and friends, and indeed representatives of the universities and members of the mathematical community to the Academy to celebrate this prestigious achievement. Thank you also to our sponsors IBEC for continuing generous support. Mr. Danny McCoy, member of the Royal Irish Academy, and colleagues indeed have joined us here today and kindly hosted this morning's masterclass for prize-winning students. Indeed, yesterday evening, in a change to the normal Hamilton Day, we hosted a very nice dinner in Trocaderos, as it turns out, to host our guest speaker, Professor Laura DeMarco. So Hamilton Day is now turned into Hamilton Days. So this is only number 2. Yesterday was number 1. And from a personal point of view, I've got a ticket to see Hamilton tomorrow evening in the Bord Gáis Theatre. So I'm interested to see the rap version of William Rowan Hamilton and how that all works out. But certainly by Friday, I will have had enough of Hamilton, I'd say, to last me another year. Thank you also to our media partner for Hamilton Day, the Irish Times, who promote the Hamilton Lecture in their paper and print. And there's an interview each year with a Hamilton speaker, and I know Dr. Claire O'Connell has already done and written that. And the interview with Professor DeMarco is forthcoming, so watch this space, as I say, to look out for that. So I'll now hand over, without any further ado, to our chair for this evening's lecture, Professor Sinead Ryan. So Professor Ryan is Professor of Theoretical High Energy Physics at Trinity College in Dublin and has recently taken up the post of Dean of Research there. She's held visiting professorships in the US and also the EU and is a life member of Clare Hall, Cambridge. Professor Ryan was elected to the Royal Irish Academy in 2023. Sinead, over to you.
It's a great pleasure to welcome everybody here this evening to this very beautiful room for the Hamilton Lecture. And it's my honour to chair this lecture this evening and to introduce our speaker for this evening. Our speaker is Laura DeMarco, who is Professor of Mathematics at Harvard University and Radcliffe Alumni Professor at the Radcliffe Institute. Her research is focused on algebraic dynamical systems with an emphasis on notions of stability and bifurcation. Professor DeMarco was elected to the National Academy of Sciences in 2020. She was awarded the Alexanderson Prize from the American Institute of Mathematics and the Satter Prize from the American Mathematical Society. Professor DeMarco is a Fellow of the American Mathematical Society and serves on the advisory board of Quanta magazine. And maybe for those of you who may not be familiar with Quanta, it's an online publication which does wonderful, and I highly recommend it, work in science communications and science outreach. Prior to her arrival in Harvard in 2020, she was the Noyes Professor of Mathematics at Northwestern University, and she's also held positions at the University of Chicago, the University of Illinois, at Chicago, and at the University of Chicago. So tonight, Professor DeMarco's lecture will explore, as you can see on the slide, the title slide, the geometry and algebra of the Mandelbrot set. And here she will consider how our in-depth knowledge of this captivating and complex mathematical concept has provided insight into seemingly unrelated research also in geometry, in dynamics, and in arithmetic. It's going to be a wonderful and interesting tour de force, I'm quite sure. She will speak for about 45 to 50 minutes, and afterwards then we'll have some time, about 30 minutes or so, for questions and answers. So without further ado, I will hand you over to Professor DeMarco. Please join me in welcoming her.
Thank you. Thank you very much for that introduction, and thanks to all of you for coming. I don't usually give mathematics lectures behind a podium, so I hope it's okay if I walk around and move around and get, have some interaction. I wanted to share before I begin that after I was invited and I began to prepare this lecture, I was really struggling to decide what to speak on, because of course I'd like to speak on something that's interesting mathematically to me, but that could also be interesting to non-mathematicians, but would also touch on very recent research. And so to get inspired, I did some research on William Rowan Hamilton. So I looked up his papers and tried to find information that I could find online, and realized, oh yeah, he was interested in algebra, the quaternions, of course, and then structure of algebra and geometry of algebra, but also interested in dynamical systems, Hamiltonian systems, physical systems. And I thought, oh, well then it's obvious what I should talk about. I should talk about the Mandelbrot set. He did not work on the Mandelbrot set, but I'm hoping to convey to you that how the research that Hamilton had done and the ideas that Hamilton had are somehow lingering in the background as I describe what I do about the Mandelbrot set, and specifically as I titled it, The Geometry and Algebra of the Mandelbrot set. So just to begin, I should say this is one of the most famous images, I should say, one of the most famous images in mathematics. It's all over the internet. Here I just did a search for the Mandelbrot set online, and you get all sorts of beautiful pictures. I imagine many of you have seen these pictures. They're very famous, even if one doesn't realize what they're pictures of. And so my goal for the evening is to, well, first of all, to answer a few questions. So to tell you what it is. So what is the Mandelbrot set? I will spend a few minutes to tell you what this picture is of. But I'd also like to explain why is it interesting? Not just why is it interesting to mathematicians who have been studying it deeply for 45 years already? That's a lot of time to spend on one picture. So why are mathematicians still interested in it? What are we doing today with this object? And in short, the answer is that it's connected to lots and lots of different areas of mathematics, including the areas that Hamilton was interested in. So I mentioned algebra, and Hamilton spent a lot of time, I understand, thinking also about the complex numbers before advancing to his thoughts about the quaternions and what is the geometry of the complex numbers, thinking of this as a two-dimensional space, and then, of course, ultimately landing on the idea of the four-dimensional number system, which he called the quaternions. But also, and what he is perhaps most famous for in mathematics now are, say, the Hamilton equations and the role that they play in understanding physical systems, our real world. And the area of mathematics that I work in, namely what we call dynamical systems now, is very much inspired by these ideas that Hamilton had. Okay, so the Mandelbrot set. So here's a picture of it. So what is it? It's a set depicted in the black here. The black part of this picture is the Mandelbrot set, and it lives in the two-dimensional plane, or it's a subset of the space of complex numbers. So to give you a sense of scale here, I've put 1 on the real axis, which is of course the x-axis here, and on the y-axis represents the purely imaginary numbers, and up here you have the number I. So this is the scale of this picture. Now what is this a picture of? So each complex number, let's call it C, each complex number determines a particular sequence of numbers, I've called them Z0, Z1, Z2, Z3, etc., generated by a very simple recursive relation. So one starts with 0, and then because the complex numbers are a number system, we can add them, we can multiply them. One can take whatever number you start with, square it, and add your chosen number C. Okay, so for each complex number C, I get a sequence of numbers. All right, each complex number, I get a sequence of numbers. By the way, this sequence, in the language of dynamical systems, imagining a planet orbiting around the sun, this sequence should be thought of as an orbit. So for each number C, I have an associated orbit that starts at 0. And the Mandelbrot set, very simply, is the set of complex numbers here in the plane for which that orbit is bounded, for which that orbit does not go off to infinity. In fact, very concretely, it's the set of complex numbers C for which that sequence never gets bigger than 2 in absolute value. Okay? So it's just that, just the set of numbers C for which this associated recursive sequence stays small. Very, very simple definition. Very simple definition. Okay, so why on earth would this be interesting? What is it about it that we actually care about? And why does the picture look like this? So again, this is the set that you're seeing in black. Notice I've traced it with colors so that you can see some of the structure of the set. But the set itself is just the part that's in black. So there are a lot of questions that one could ask. And as I said, so why would this be interesting? Well, it turns out that this set comes up in many different ways. So I've given you a definition of the Mandelbrot set, but there are other ways to define the Mandelbrot set. In fact, there are many different ways to define it. And this is one of the things that makes it interesting, I should say, to a mathematician, is if you arrive at the same object from many different paths. So here I gave you a simple recursive relation, but one could give a more sophisticated approach. We think of this Mandelbrot set as something called a bifurcation diagram associated to that family of recursive relations. I won't give a formal definition, but for me, I think of it as a bifurcation, a picture of the bifurcations in some particular family of dynamical systems. But it turns out that although it was defined for this very particular, sorry, can you see if I'm standing in the way? It was defined for this very particular system, just with these degree 2 polynomial recursion. This is very particular nonlinear recursion. It turns out that you could replace this particular quadratic polynomial with a whole bunch of other examples, cubic polynomials or rational functions or sine functions or other examples. And you will, when you draw the corresponding bifurcation diagram, you will also see Mandelbrot sets in your picture. So it turns out to have this universal property that it comes up over and over again with lots of different examples, lots of different formulas, lots of different equations, which is one of the things that makes it especially interesting to us as mathematicians. Okay, so I would like to share a little bit of history of it before I get to the recent work. Perhaps the very first mathematical theorem that was proved about this set was in the very early 1980s, which is the statement that the set itself is connected, that it's one landmass, and there aren't little islands off of the edge of it. It's really just one landmass. That's what we mean by being connected, which is not at all obvious if you draw pictures of it, mind you. Of course, computer graphics have come a long way since 1979 when this image was generated. I love this image. Computer graphics have come a long way, but even so, I plotted this myself just using very low resolution on my computer, and you can see it definitely does not look connected. You can see all of these little black dots, all the dust around the Mandelbrot set, which really suggests, on the contrary, it shouldn't be connected. And that would have a significance. Of course, there's a reason I might be interested in connectivity, and that's another talk, perhaps. But okay, so it turned out it actually is connected, so those little dots aren't there. But here, this is interesting. So that was a low resolution picture. Here, by the way, this is one of the images that Mandelbrot, who the set is named after, printed in a publication in 1983. So already, I mean, within a few years, computer graphics were significantly improved. And Mandelbrot, who called this set the M set in these early publications. By the way, I put Mandelbrot set in quotes up here because in 1981, it wasn't called the Mandelbrot set. That was a name that was given to it later for the work that Mandelbrot had done, and who was really advertising, shall we say, advertising the importance of this set, and did a lot of good for saying how interesting it is, and hey, mathematicians should really take a look at this. And so he called it the M set, and we today call it the Mandelbrot set. So that's a slightly more recent image, but of course you can still see the little black dots around the set. Here is a picture that I drew myself recently on my computer with higher resolution, and it still looks very disconnected. But I don't know if you can see this from where you're sitting. Those little dots, they resolve themselves. Can you see those shapes? They're actually little tiny copies of the Mandelbrot set itself. So that's what happens when you increase the resolution. You don't make it look more connected. It will never look connected, even if you have a very, very powerful computer. If you draw it this way, you'll just see the structure better. You'll see that you get the little copies, that this set has some kind of self-similarity features to it. But so this is one of the reasons, by the way, that you see all those beautiful pictures. If you start to add the colors, then the structure of the set really comes through. And you can see now from this picture, you don't see the black coming through, but the colors indicate that there has to actually be, we're buried very deep in there, some kind of connected thing, like some kind of way to get from this main landmass out to what appear to be islands, but are not in fact islands. So this picture, by the way, is produced with a very, very simple algorithm. It's something you could do at home. One simply takes each pixel, call it C, and start creating those sequences, and then just check, as I said, check if it ever gets big, say bigger than 2 in absolute value, but color according to how many steps it takes to get out to a definite size. So the pink means maybe after 1 step or 2 steps, it jumps out to a definite size, and yellow means it takes longer to get out. So the different colors correspond to what we call the escape time. How long does it take to escape the size of your sequence to get big? So it's a very simple algorithm, and this is the algorithm that most people use to draw the pictures, and you see all these lovely images online, and so the pretty pictures are not just pretty. There's a reason we use them. It's because that structure is just invisible unless you use the colors or some way to shade your image. Okay, so that was just a little bit about the picture. What was next? Oh, I forgot. I included one slide for the mathematicians. One slide for the mathematicians here. The proof of this theorem is very short. That's the whole proof right there. It's just a little bit of complex analysis, and I know there are some mathematicians here in the audience, so just a quick remark. The point is, of course, that these recursions, which are defined by quadratic polynomials, there's a nice holomorphic or analytic dependence on both the parameter c and the input variable z. And so one can use the iteration, the recursion, to define a conformal isomorphism, or what we call a Riemann map, to the complement of the Mandelbrot set. So the complement turns out to be isomorphic to a punctured disk. So just a quick mathematical remark. The proof is very easy. I say the next really significant result about the Mandelbrot set is what we call its universality. So I mentioned this earlier, that the Mandelbrot set comes up not just from studying that particular recursion with quadratic polynomials, but many other examples as well. So what does that really mean? So even in the family, in this particular family, why do we see these little copies of the Mandelbrot set? Why would we see the little copies of the Mandelbrot set? This is not obvious. It's not this fractal picture, what we call a fractal picture, is not actually self-similar. It's not actually self-similar. There is no, if you've ever studied fractals, maybe you've generated fractals yourself, and how do you usually generate them? You define some sort of iterated function system. You have some dynamics in your space, and you have some repeated operation. You repeat, and you end up with some image in the limit. This is not that. There is no iterated function system generating this picture. It is not one, there's no dynamics on this picture. This is what we call a parameter space picture. This is representing a space of dynamical systems. Those dynamical systems live somewhere else. This is a space of them. So there is no dynamics on this picture. So it's actually surprising that those little Mandelbrots are there. And it took some real work, it took some real work to prove that those are genuinely copies of the Mandelbrot set itself. And the theory that we use is what we call renormalization, which is named after some physical theories. But here it's really referring to the idea that, that certain ones of these certain examples, so for certain values of C, those recursions, those sequences that you generate, you can start not just with 0, but with different points, that they themselves have, how shall I say this? I say this in an accessible way. But they have this renormalization property, is what I want to say, which often means in a given system at a very small scale, and in the long term, the system behaves like it did on a large scale. So the big picture scale is repeated at small scales, but in the longer term time. And so what happens is that for certain values of C, for certain ones of these recursions, you get sort of little copies of the whole big picture happening, but not in this picture, in their own dynamical plane, which I will not describe. So the renormalization theories actually go very, very deep, and they're one of our most powerful tools now for studying the Mandelbrot set. I should just mention, I mentioned just a few of the names who contributed to this in the early 80s, in the first half of that decade. I picked out, so people have continued to prove what we call renormalization theorems up until today. It's still a very active area of research. And I did pick out the work of my own PhD advisor, McMullen, who published an article with this as the title, The Mandelbrot Set is Universal. So I'm giving him credit for the words that I'm choosing here, the Mandelbrot Set is Universal. Who then went on to prove not just why you see little copies in the Mandelbrot set itself, but that you also see these Mandelbrots for other families of systems. That's the important part. In fact, I have a few pictures to show you some examples. Maybe one of the most famous examples of this is the systems that are generated by what's called Newton's method. I don't know if you remember learning about Newton's method in a calculus course, which was this iterative strategy for finding roots of equations, f of x equals 0, to numerically solve for the x, where f of x equals 0. And of course, now you can just enter it into your computer, and your computer will give you some answer to 50 decimal places. But what system, how is the computer actually generating that answer? Well, one of the ways to do it is by what's called Newton's method. But Newton's method doesn't always work. You have to have a good guess. I don't know if you recall this, but in Newton's method, the way you try to find the roots numerically, you input some initial guess, and then you run some recursive process, and then if you're close enough to start, then it will converge to the actual root. I don't know if you remember that, but in Newton's method, if you make some guess which isn't close enough, your sequence could do something very different and perhaps never converge to a root. But how do we nowadays understand the failure of certain sequences to converge to a root in Newton's method? It turns out there's a hidden Mandelbrot set in that story which explains why certain starting seeds don't converge to roots. There are in fact entire, shall we say, open sets of starting points that fail to converge to a root, and part of it is the reason for such failure, for dramatic failure indeed, even among degree 3 polynomials, are little copies of Mandelbrot sets in the bifurcation diagram associated to Newton's method. And just for fun, I included on this side, so this is a story that's been known for a number of years. Newton's method, actually, I'm not even sure if it goes truly back to Newton. Maybe it goes back to the Babylonians. In fact, probably goes way back. But the study, this aspect of understanding Newton's method was certainly understood in the early 1980s when people were beginning to look at the Mandelbrot set. This picture here is an example from my own work where I was looking at some other family of recursions. It doesn't matter what the formula is, but there was some formula, and I was trying to understand how they bifurcate. And this is a picture of the associated bifurcation diagram, whatever that means. But I know by universality that there have to be Mandelbrot sets somewhere in this picture. And while this sort of eye shape has some Mandelbrot-like features, it's not a Mandelbrot set. It's not itself actually a copy of the Mandelbrot set. But it turned out that if I zoomed way in and if I know where to look, I could find little copies of the Mandelbrot set. So if you can see this is a very distorted copy of the Mandelbrot set. Its head is way over on the side. So this, I knew it had to be there, but I had to zoom way in to find it. Now, these Mandelbrot sets by universality are in fact everywhere in that black region. It's just that they're small and sometimes in practice hard to find. So it's just one example to show you that they really do show up in other settings. So you could come up with your own formula for a recursion and explore it and find Mandelbrots themselves. Okay, so the Mandelbrot set is intriguing. It arises in many different settings. But I think the most striking thing, especially for non-experts, is that we still don't understand it. We still do not have a complete description of it as a set. There are a lot of features about it that we can explain, the small copies and a lot of the sort of numerical aspects of it, a lot of topological aspects of it, but we still don't understand it completely. And by completely, at least for the mathematicians, I really mean a complete combinatorial, say, understanding of every one of the components of the interior of the Mandelbrot set is what we would like to describe. So can we give a complete description of the Mandelbrot set? Now, a more formal way to put that, and again, as I said, I know there are some mathematicians in the room, so let me just say, here is one way to formalize this question. There is a conjecture that really goes back about 100 years, but was revisited by Duodie and Hubbard in the 1980s. The formal language for what I'm asking is the following question, is the following belief. That's the word conjecture. This is believed to be true, but we don't know how to prove it, which is that the dynamical systems, the recursions defined by these quadratic polynomials, should be what we call hyperbolic for what's called a dense set of C values. we expect, in layman's terms, we expect most of these examples, most of the recursions, most c-values, to be simple. The hyperbolic ones are the simple ones. So we'd like to be able to prove that most of them, in some topological sense, most of them are simple. And we just don't know how to prove that. By the way, I have one picture to, oh, I forgot I put this up. So, Sinead mentioned the Quanta magazine. Since I'm on the advisory board for Quanta magazine, a little plug for the magazine also. They put out earlier this year, an article on the recent work on the Mandelbrot set, specifically towards trying to prove this conjecture. There's a stronger conjecture, a stronger result, which of course we still don't know how to resolve, is proving that the Mandelbrot set is locally connected, which would imply also this conjecture. And there are a number of mathematicians who are actively working on it, and there's a great article in Quanta which features some of those mathematicians, and I encourage you to take a look. Okay, but the next slide, there was a picture here I wanted to show. I've colored the interior regions of the Mandelbrot set here according to some features of the recursions that the c-values define. So for example, in this orange region here, for each of those sequences, now remember the definition, for any given point C, any given complex number C, I've generated that string of numbers, that sequence of numbers by the recursion. If that sequence actually converges to something, has a limit, the numbers just approximate some given point, if that happens, color orange. If that sequence in the long term appears to bounce back and forth between two values, color yellow. If it appears to bounce back and forth between three values in the long term, color this shade of light green, etc. So each of these colors correspond to what is the behavior of that sequence of numbers. Does it appear to have some limiting behavior where it cycles in some way? And according to the length of that cycle, or what's called the period of that cycle, that's what these colors are. So we expect, another way to think about this conjecture, we expect that every interior region has a color. We expect that every interior region has a color in this sense. But it's possible that if you zoom in somewhere, you'll find a region that stayed black, in the sense that that sequence never appears to cycle in the limit. Maybe it's bouncing around randomly in some region. Okay? We don't know how to prove that for all of the interior regions, the sequence will eventually look like it's cycling. Okay? We don't know how to prove that. There might be what we call those ghost components. There might be a ghost component in the Mandelbrot set. We don't know how to prove they don't exist. But there's been so much work on this. Oh my goodness, so much work on it. As I said, 45 years of just thinking about this. In fact, even more if you go all the way back to the work of Fatou and Julia and other mathematicians who worked on it before they had computers to play with. There's been a lot of work on this, and it's still open. But I'd like to share with you, let's see, what time is it? 6:30. Oh, I forgot to start my timer to know when I began. Do you know what time it was when I began? Okay, thank you. Good. So I want to share with you a little bit of the work that I'm doing related to the Mandelbrot set and how we're trying to bring in new tools to analyze this problem. I cannot answer this problem, I will tell you now. I'm not going to resolve this conjecture today or tell you that or announce a proof. I wish I could. But I would like to take you a little bit deeper into the study of the Mandelbrot set, just a little bit deeper. So let's look a little bit more at the structure of this set. There are some distinguished points inside this Mandelbrot set. Now remember, the entire black set corresponded to the C values for which that sequence generated in this way is bounded, okay, which doesn't get big. But there are some distinguished points here. There are some distinguished points here that I've plotted in yellow, which correspond to the ones where 0 comes back to itself. So it's already in a cycle. Okay, so 0 itself is in a cycle. So that's what I've plotted here in yellow. And I've got some examples. Right here is the point C equals 0. And when you plug in c equals 0 and you run this recursion, of course the sequence, it's not moving, right? 0 goes to 0 goes to 0. So it's in a cycle of period 1. Whereas over here, this is -1, c equals -1. And if you just take a look at what that does, when c is -1, 0 goes to -1, which then -1 squared is 1 minus 1 goes back to 0. So here I'm in a cycle of period 2. And remember my colors, each one of these regions corresponded to a sequence that looked like it was eventually cycling. There's actually only one yellow dot in each of those regions. That's easy to prove. There's only one yellow dot in each of those colored regions, or I should say, at most one yellow dot in each interior region, which is easy to prove. And those are what we call the periodic C values, or even we call them centers. They sort of play the role at the center of that region. Okay, so going back to that initial question, sorry, I can rephrase it in terms of these yellow dots. So remember the original question, can I give some complete description? Really wanting to know, is every interior component simple, nice, hyperbolic? In terms of the yellow dots, what I'm really saying is it true that every one of these interior regions has a yellow dot? Okay? I want to know that there's a yellow dot in every interior region. So what can I do with these yellow dots? How can I study these yellow dots? So we've been playing around with properties of these yellow dots. I guess that's how I should describe this particular project. For example, I've been trying to understand, oh, that's terrible formatting. I've squeezed those words in the top. What is the geometry of these dots? Is it possible that, wait a second, sorry. That's not what I meant to press. Special points, what is the geometry? Oh, that's what I'm looking for, okay. Are there various patterns of the yellow dots themselves, beyond what we see that they happen to be inside the Mandelbrot set, but does the location of these dots, which the points themselves satisfy some important properties, do the locations of these dots tell us something? Are there restrictions on where they can be located? Maybe some features of these dots will tell us more about the Mandelbrot set. And so this next image was supposed to show sort of an example. What do I mean by what is the geometry? Really Euclidean geometry, I mean, just the structure of this inside the plane, in the way that Hamilton thought about complex numbers as couples of real numbers as inside this two-dimensional plane, and we have an associated geometry there already. So what can we say? For example, we know that any pair of dots is on a line that we know. 2 points determine a line from Euclidean geometry. Okay, so any pair can certainly be on a line, but can there be more than 2 dots on a line? Can there be more than 2 dots on a line? Or should we expect that these dots are basically thrown down at random in some way? There are some symmetries. The picture is symmetric about the x-axis. So if I have a picture of dot on the bottom, I have a corresponding dot on the top. So certainly, as we know, there are vertical lines that have 2 dots. But could it be that there's a vertical line that happens to pass through more than 2 dots? Okay, so that's what I'm asking. A vertical line or any other line that passes through more than 2 dots. Now there is one, I hope, obvious one in the picture. If you haven't ever studied this, and maybe it's not obvious, but you can really see right here that the horizontal line has a few what appear to be, I mean, my dots are so big, it's hard to tell where they're centered. But there are actually, it turns out, infinitely many yellow dots on the real axis itself. So this Mandelbrot set, I said, it has this self-similarity feature, even though it is not actually self-similar. There are little copies of the Mandelbrot set all along this antenna here that go out to the point -2. You'll see little copies of the Mandelbrot set. And on each of those, you will also see all these same little dots on the copy. So we have lots and lots of yellow dots along the x-axis, or the real axis. Okay, lots of them. So we know that there are infinitely many on the real axis. Okay, so certainly there can be at least one line with more than 2. Okay. Here's a result proved in this direction, published in 2017 by some mathematicians, which tells us that actually that real axis is the only line In fact, for the mathematicians, let me emphasize, the only real algebraic curve in the plane, which contains infinitely many dots. We won't find other lines with infinitely many dots, which I should emphasize is already surprising. Remember that these baby Mandelbrots are everywhere, everywhere, dense on the boundary of this Mandelbrot set. You'll find them anywhere you zoom in. But you will not be able to, shall we say, skewer those yellow dots on any of those copies. This is the only line that has infinitely many. So on all of these, what it means is that all of them have a little bit of distortion. They're all a little bit askew. So you will not be able to have little lines, which is a really interesting result about the geometry of this renormalization theory, as it can be interpreted in this way, how these little copies are not, they're not straight. Most of the renormalization theorems, I should emphasize, actually go the other direction. They're also not too distorted. I showed you a baby Mandelbrot in one of my pictures that was really distorted, where the head was like way over on the side. But most of those copies actually look almost the same. Even this one here is actually slightly distorted, but from the original. But it's almost the same, and that's sort of one of the power of those renormalization copies. The theory is that the distortion is controlled. And that's actually very useful in a lot of studies, both of these systems and other systems. But there is definitely distortion, as for example, this theorem shows. You cannot skewer that middle line, those yellow dots up there. So that was interesting. But that didn't really answer my question. I said, what about 3 dots on a line? Or what did I write there? Or 10, or maybe 127 yellow dots. Is it possible to have configurations of these points that aren't infinitely many? So maybe finitely many, but not too many. But more than 2. So I should say, we don't know how to answer this question. We actually don't know how to answer this question. But in some very recent work, in a project that I just completed last year, together with one of my collaborators, Mirto Mavraki, who's now in Toronto, we were able to, I forgot to say something, but I'll finish my sentence. We were able to make a little bit of progress in this direction. But I should say, it just sounds, it sounds crazy because this seemed to be such an elementary question about the Mandelbrot set, this thing that we've been studying for so many years. But even this result about the infinitely many yellow dots was already very difficult for them to prove. There are a lot of techniques that go into their proof, a couple of which I'm hoping to say a tiny bit about, if I don't run out of time, to say a little bit of what mathematics goes into it, but really techniques that were only developed very recently. And so in the work that I was doing with Mirto Mavraki, here's an example result. It's an example result that we were able to obtain in this direction. So we tried to understand, can there be lines with 3 dots? Can there be lines with 3 dots? And what we were able to prove is kind of a very weak result in this direction, which is, well, maybe there can be lines with 3 dots, but there are only finitely many of them in the plane. I don't know how many, nor do I know how many dots would be on those lines, but at least I know there are only finitely many of them. So this is, well, it felt like this big step towards answering this question, but really we can't get very far. And let me emphasize that even this result required techniques that were only developed within the last 3 years, really using very recent machinery and a lot of the recent mathematical tools a lot of things that we could get our hands on, and we still only got this far. And as I said, I don't know what any of the exceptions are. And again, in other words, the only known example of a line that has more than 2 dots is this one, which has infinitely many. I don't know of a single example of a line that has 3 dots if it's not the real axis. So that's a pretty sad state of affairs. But Okay, nevertheless, it's been a lot of fun. And so the joy of this project is, something that's was very hands-on. It was this very explicit example setting. But I want to tell you a little bit about what the mathematics is, because the mathematics we're using and what we are actually proving has nothing to do with the Mandelbrot set. Okay, nothing at all to do with the Mandelbrot set. What we're really interested in, going back to Hamilton, are connections between algebra and dynamical systems. These interests that he had, complex numbers, quaternions, number systems, shall we say. So generally speaking, the concept of a number system where you can do addition, multiplication, division, especially, number systems, and how those number systems arise very naturally in certain types of dynamical systems. So this final slide, which is a little bit long, but okay, I'm good. Okay, good. So this last slide, I want to feature some of the mathematical ideas, try to explain them, just that go into an argument of this sort. It's kind of a silly statement, honestly, to be talking about lines in the Mandelbrot set, but there's so much more to it. So as I said, it was really about understanding how the algebra of the system, which remember they were defined by degree 2 polynomials, those recursions, how the algebra of the system restricts the geometry and the shape and the topology, etc. Like what restrictions do you get from the algebra? And this is something that I'm personally very interested in. And maybe Hamilton was also interested in. I know he wanted to use his quaternions. I don't know that they were used maybe in the way that he was hoping and still have not been. But I'm not using quaternions either, but other number systems as it happens. So, okay, algebra, number theory, arithmetic geometry. And as I said, the techniques are not about the Mandelbrot set. So this is a picture of some other family of systems. In fact, a picture that comes from a particular family of elliptic curves, really studying a totally different thing. There are some dots in the picture. The tools apply also to pictures of this sort with their own special points and their own special dots. But let me stick with the Mandelbrot set. There's no reason to go more general. So in this slide, I've just mentioned a few of the mathematical ideas, concepts, just a few of the concepts that go into these arguments. And what are some of the key ideas? So the algebra, really the algebra is the most important here. So what's special about those yellow dots? One of the things that's special about the yellow dots is that they are what we call algebraic numbers. Algebraic numbers. And what does that mean? That means that they're zeros or roots of polynomials that have integer or whole number coefficients. They are roots of polynomials with whole number coefficients. And what polynomials are they? In this particular case, for the Mandelbrot set, okay, I have my recursion defined by a degree 2 polynomial. One can compose these polynomials with themselves, so they're still a polynomial. But if you think of this as now a polynomial in the C variable, where you evaluate these guys at z equals 0, remember that my recursion started with 0. So I evaluate these compositions at 0, and that is some polynomial of some large degree. Oh, I put an n here, which meant I was supposed to take n copies of, I was supposed to compose with itself n times. And that it would then be a polynomial of degree 2 to the n, approximately, or 2 to the n minus 1 in C. Anyways, these are polynomials. It turns out they have integer coefficients as functions of C, and those yellow dots are their roots. Okay, so that's something already a special feature, this integer feature. But it's even more. Not only are they algebraic, they're low complexity numbers. They have low, what we call arithmetic complexity. And the technical language here is their points of bounded Weil height. André Weil, who introduced a way to measure complexity of numbers. This was heights, I believe, were introduced in the context of studying elliptic curves. For some work that he had done in the 1930s, I suppose. Hopefully I have that history correct. But But we use what we call Weights to study complexity of a number. Okay, so for example, complexity of a number. Suppose you have a fraction, a rational number, so a ratio of two integers, a over b. I have it in reduced terms, so let's say no common factors. So it's written as simple as possible, 1/2 or 1,000,000 over 1,000,001. The complexity can be measured, it turns out, by this formula. You take the largest of the two, and I'm working with a logarithmic complexity, so I take its log, although this you don't really need. What does that represent? Roughly speaking, this number is approximately the same thing as how many digits does it take to write this number down? So complexity in that sense. How much information, how much space on your computer do you need to record the data of that number? Is a modern way to think about this notion of height. And this is the definition for a rational number. And then there are versions that work for all. There's a version of this formula that works for all algebraic numbers. But again, you should think of it as how complicated is a number? How much information is required to understand that number? And all of these yellow dots, it turns out, have very low complexity, near zero complexity. Not quite zero, but close to zero complexity. And that low complexity feature turns out to be a very powerful tool in understanding their geometry in the plane, at least for this particular problem. Because there's one more fact, which now I've formulated it as specific, really specific to the Mandelbrot set. Well, I've formulated all of this as specific, but in this particular case, I've written it in language of probability and measure theory. But the statement is that those yellow dots, they're random in some sense with respect to some particular distribution. They are uniformly distributed in my picture, not with respect to area. No, they're not thrown down at random in the way you and I might think as throwing down points at random, where they would be sort of really uniformly distributed. They're uniformly distributed with respect to a very particular distribution, which is living on the boundary of the Mandelbrot set. So it turns out one can prove, the statement that I've written here mathematically is that you look at all the roots of this polynomial, you put a single mass on each one of those roots, you normalize, so you have total mass 1, and then you let the set grow. You let n go to infinity, and you have this collection of dots that are getting spread out more and more towards the boundary. The uniform distribution statement. That was proved in the 80s, by the way, by Levin. It's not my theorem. But it turns out that these facts together combine to give that restriction on the geometry that I was referring to. So the way that the actual logic of the argument is, I wanted to prove there are only finitely many lines with at least 3 points. So by contradiction, suppose you have infinitely many lines with at least 3 points. Each individual line is a relation between those 3 points. That's a linear relation between those 3 points, sort of by definition. Now, infinitely many, the 3 points, the relations could be different. On every line, maybe it's a different relation. But the low complexity means, somehow implies that actually all those relations were the same relation. It's not a different linear relation on every line, but it's the whole family of lines has one giant relation, so there's some kind of big symmetry of the whole picture. Which shouldn't be, because my Mandelbrot set is not self-similar. I wrote it, I've sort of phrased it down here. The Mandelbrot set is not self-similar. You have copies of the Mandelbrot set, yes, but the entire thing is not actually similar. There is no angle preserving, is the word conformal here. There is no way to really have a copy of this part of the Mandelbrot set look the same as this other part, unless you're flipping it over the real axis, which is why the real axis is an exception to this rule. The real axis is special, because it is a line of symmetry that actually exists. But the real axis is special. And so that, I believe, concludes, in fact. In fact, you should give me a 5-minute warning. But I think this is the end, because that's what I wanted to end with, was just those words. Oh, no, I have some references. It's way too small, you can't read it anyways. But this was the end of the paper that I had written on this particular lines in the Mandelbrot set example comes from this work with Mavraki, and that was the title of the paper, and those are just some of the references that I wanted to share, so I can share my slides with you afterwards if you're interested in some of the references. Thank you very much.